Welcome to this video on statistical mechanics. I am Jos Thijssen and I teach statistical mechanics in the Master Program Applied Physics at the Delft University of Technology. In this movie I want to address the Langevin equation, which describes heavy particles that are surrounded by light particles, so it could be smoke particles in a gas or solute particles in a solvent, and these heavy particles, they experience collisions from the light particles, and the effect of these collisions, we want to capture that in a force, which is a frictional force and a so-called random force, which is also called the Langevin force. And the resulting equation of motion is called the Langevin equation of motion. We make several assumptions for the random force, for the Langevin force, and from this we can calculate many properties, and the most important one is that we can derive the evolution equation for the velocity distribution in such a system. So that means that we look at the distribution of the velocities of the heavy particles, and we can see how that evolves in time. And as we will see, it will evolve towards the Maxwell equation, which is not really surprising, but the equation which describes this evolution, it's the Fokker Planck equation, also describes how a non-equilibrium system evolves towards the equilibrium Maxwell distribution. I hope you enjoy this movie. Here you see a molecular dynamics simulation of a Lennard-Jones gas. Those are atoms which interact via a Lennard-Jones potential, attractive well and a repulsive core. And the particles are atoms, they are rendered by blue dots, but there is one particle which has been singled out, that's this blue particle here. And the blue particle is just one of the atoms, it's an arbitrary atom, and by giving it a different color it's easy to see how it moves through the gas. And as you can see, it's a kind of random walk motion. The particle receives kicks from the other particles, and that moves the particle, the blue particle, around. And we shall see that although the motion for each individual particle is completely impossible to predict, it's possible to make definite statements about the motion in general that the particle makes. So we can make statistical statements about that motion. And that is the subject of this movie. In fact, we focus on the special case where we have a large particle, that's this disk here, which is moving in a dense gas or fluid consisting of small particles, and they bounce off this large particle, and that gives rise to the famous Brownian motion, and its motion is determined by the light particles which collide many times with the heavy ones. So the disk is moving slowly and the other particles are moving a lot faster, because equipartition tells us that the kinetic energy is equally distributed over the particles. But a heavy particle then has a much smaller speed. The effect of the collisions by the light particles with the heavy particle is twofold. First of all, the heavy particle will feel a drag. You can imagine that if the heavy particle moves at some speed through the liquid, it will experience many more head-on collisions. Then it will experience kicks in the back. And therefore its speed will slow down until it comes approximately to a rest. So the first force that the heavy particle feels is a drag force. On top of the drag, it will feel random kicks in all possible directions, and so you have random kicks on top of a drag. So first of all we have the drag, and then there are random kicks that even if the particle has come to a rest, there is no drag anymore, but there will be random kicks in all kinds of directions. We want to capture the effect of both the drag and the random kicks in an equation of motion. The drag force is easy to incorporate because we know its form, it's minus gamma times v. That's the usual form for the drag force. Then the random kicks, we represent them just by a force r, which is a vector, and it must have some random character, and that represents the random kicks. And eventually there is a field like gravity, or if the particles are charged, it may be an electric field, which is a systematic force. And we can include that, and we call it F, depending on position and time. So the F is a systematic force. The drag force and the systematic force are rather familiar, but the same cannot be said of the random force. However, although the random force itself is by nature unpredictable, we can make some statistical statements about it. So we can make some statements about the statistics of the random force. The first property of the random force is that its expectation value is equal to 0. For all times. So imagine the fluid or the gas being at rest, which means that its center of motion is at rest. Then obviously if I put a particle in, and I put a particle initially at rest, it will get random kicks from all directions, and these will average out. That's an average in time. So what does the average here with the angular brackets mean? Because this is evaluated at one particular time t. Well, the average expressed by these angular brackets is an average over all the possible realizations of the random force. So if we start a simulation or an experiment, we get a certain random force, then we do it again and again and again. So we have a long series of random forces at subsequent times. And if we average over that series, then it turns out that this random force is 0. So the angular brackets represents an average over all the possible realizations of the random force. The second property of the random force is formulated as a statement about the correlations. So imagine we take the random force at some time t, at some arbitrary time, and then we take the random force at some time tau later than t, so t plus tau. In that case, the expectation value averages out to 0 whenever the tau is greater than 0. So when we look really at a later time, the random kicks have nothing to do with the random kicks that you saw before. Now in a liquid we know that is not true, because in a liquid you have hydrodynamic correlations. So this is an approximation, and in fact that approximation is valid for heavy particles, because they will experience many collisions before they change their position appreciably. So if the time scale at which the heavy particle moves is a lot slower than the correlation time in the fluid, this is a good approximation. However, if I take just one atom feeling random kicks by the other atoms, it turns out that this assumption is not valid. So why do we make that assumption? It's for mathematical convenience, because it enables us to infer all kinds of properties without too much mathematical effort. This is therefore an approximation that is made very frequently. So it says that the correlations between subsequent random forces vary. Of course, if tau is 0, then I just have the expectation value of the random force squared. The final property of the random force is that it's subject to a Gaussian distribution. So each force is drawn from a Gaussian probability distribution. PR represents the probability density for finding a random force of size r. This should in fact be a vector, but you can read this as one component of r. So each component of r is subject to this probability distribution, which means that if we run, for example, a computer simulation, we draw a random force at each time from a Gaussian random distribution, and then we feed that into the equation of motion. And we do that for each component, so that's why r here is not a vector but just a number. When discussing random forces, it's anyhow convenient to think in terms of a computer program, and in a computer program what we do in order to solve the equation of motion is to discretize the time. So we have time steps t1, t2, etc. They are equidistant, which means that the distance in time between two subsequent time steps is always delta t. In the simulation we generate a random force for each time step, and the properties that we have formulated before translate into the following recipe. The probability density for having a random force R1 at time t1, R2 at time t2, etc. is given by this expression, which is a Gaussian expression, and the fact that the forces are uncorrelated at subsequent time steps just causes this probability to be the product of the individual Gaussian probabilities. We can then return to the continuum notation. We have a sum over r's at subsequent time steps. We can formulate that as an integral if we divide by an extra factor of delta t. And so we have now formulated the probability distribution as a continuum distribution, and we use a shorthand notation 2q for the denominator here, and so this is our continuum prescription for the probability density of having a force between t1 and tn. If we then recall our prescription, which was that the correlation function of the random force led to a delta function, we can write for Rn, Rm, and this is now one-dimensional, that it's equal to r squared delta m and m. That's now a discrete delta function in the discrete time. It is interesting also to consider the correlation property of the random force. We can formulate that also in discrete time. Note that I have taken here a scalar r, so this is one component of a vector random force. And in discrete time, this will give me an Rn times Rm, random force at times Tn and Tm. And that is equal to the average value squared times, well, this delta function in discrete time turns into a delta Nm divided by delta t. Because the integral over the delta function is 1, we need the 1 over delta t here. And due to this property here, we see that the width of r squared is always this q. So we have a q over delta t times delta nm. So this r squared is just q based on the properties of Gaussian integrals and the second moment. Next we turn to the solution to the Langevin equation, and in general that solution is difficult to find, but in the case where the systematic force is equal to 0, we can make some statements about the solution. So that's the case where we will be now, and the Langevin equation then reads as follows. We have mv dot is minus gamma v, that's the drag force, plus r, which depends on t, and which is a random force. This equation is called the Langevin equation. The Langevin equation is a differential equation in V, and it's a homogeneous equation for one dimension, and therefore we can first try to solve the homogeneous solution. So we take r equal to 0, and then we are left with this equation, and that gives us the homogeneous solution. V wiggle is v wiggle 0 times e to the power minus gamma t over m. So this is the homogeneous solution. Then we need to find a particular solution, and we do that using the standard method. We try a solution of the form Vt is the homogeneous solution times some function that depends on time. And if we plug that into the differential equation, we get the following. First of all, we have two time dependencies, one here and one there. So we get two terms from the m times v dot. Those are those two terms, and on the right hand side we have here the drag force, and here we have the random force, and the drag force is cancelled on the left and right hand side. So here you see that this term is identical to that term, and so we are left with a simple equation for f. This equation can be directly written as f dot is some function on the right hand side which depends on t, and this can easily be solved. When I say solved, it means writing the solution formally as an integral over a function involving the random force, and because we don't know the random force, there is no way we can integrate this function analytically. Putting this f into the form for v that we have written here, we obtain the following solution. We have here the particular solution, that is the one we just found, and this is the homogeneous solution which we can add with an arbitrary prefactor. And because we take the integral from 0, this prefactor should be the velocity at time t is 0. As mentioned before, the second term is not amenable to analytic solution, but we can definitely infer some statistical properties of the solution for v using the statistical properties for r. We can, for example, calculate the expectation value of this v. We put angular brackets, which means that we average over all the possible realizations of the random force, and because the average value of this random force equals 0 for all times, the solution will just be the first part because the second part vanishes. So on average we can find what the v in the course of time is. Obviously that's the average behavior, and it's interesting to see how v would vary around this average solution. In order to find that out, we calculate the v squared of t, so that we can later subtract the v expectation value squared. That's this expression, so the difference is this term. And now we have here two r's, because we have two integrals. We have first an integral for the first v, and then for the second one we call the integrand the integration variables t1 and t2. And therefore we have an expectation value of rt1 and rt2, and we know from the statistical properties of r that we can write this as q times delta t1 minus t2, and that simplifies the integral a lot. Working out the integral, we obtain the following result. So here we have a q which now enters in front of a single integral because we had a delta function. The delta function tells us that t1 is equal to t2, so we have now 2 times gamma, and I now have called the integration variable t primed. We can carry out this integral. It's a very simple integral, and the result is that we have v0 squared times minus 2 gamma t over m plus q over 2 gamma m times 1 minus e to the power of minus 2 gamma t over m. So what do we have? We have an average behavior, and that average behavior is typically the solution to a drag equation, exponentially damped velocity, and we have also an expression for the variation. So if we subtract this term from the left and right hand side, this turns out to be the fluctuation, the average value of v with respect to its average velocity. And we see that for long times this term decays, and we are left with just q over 2 gamma m. So for long times the first term of course decays to 0, also this term decays to 0, and we are left with a constant for the expectation value of v squared. So here I've written down that very same statement. It's q divided by 2 gamma m, that's the expectation value of v squared. But if the particle is in equilibrium in a liquid or in a gas, we know from the equipartition theorem that the velocity squared expectation value should be kbt over 2 over m. And therefore we find an expression for q in terms of the temperature and the friction coefficient. So q is 2 gamma kbt. We have seen that the Langevin equation is an equation of motion in which there is a frictional force and there is a random force. We will study that equation from now on, just for simplicity, with m equal to 1. And what we want to do now is not to study individual trajectories, but we want to see what the probability is to find a particle with a particular velocity v at a certain time t. So we search an equation for this probability density, which is time and velocity dependent. So suppose we know where the particle is at t, what its velocity is. We can find the velocity at the next time step. We discretize the time now with a time step delta t, and we find that the new velocity is the same as the old velocity plus the force, which is minus gamma v plus r delta t. So let's make a cartoon of this equation. We have the old velocity, which is vt, and this first term minus gamma v times delta t, which is here shown in green, that reduces that velocity. So all the velocities are reduced by this term. And then we consider the next term. That is the term with the random force r. So we show the distribution of the random force, which is Gaussian in blue. And here we show r delta t. So this is the probability distribution for the second step, r delta t. We want to find an equation for p at the next time step. So the distribution for the velocities in the next time step, provided we know the velocity distribution in the old time step. And therefore, we have to integrate over all the possible previous velocities, and we call these now v old. So we integrate over dv old. And in addition, we integrate over all the possible steps, drt, r delta t, like this. The probability that we will have a v old is given by p v old at time t, at a previous time step. The probability that we make a jump of r delta t, we call that curly p. So this is my curly p. That's a Gaussian distribution. So please note that I have a simple p like this, and I have a curly p. The curly p is a Gaussian distribution, and we don't know what the p of v is. But of course we cannot have just any v old and any displacement v delta t, because we want to restrict ourselves to those combinations which give us the new v here. And we realize that constraint using a delta function. So here I have inserted a delta function which guarantees that this equation holds. So this is the v in this equation. So in this equation here we call this v. This is the v old. And this is also the v old. And so if I want to satisfy this equation, then I can realize that using this delta function. And because we have a delta function, it's now easy to work out the integral over the v old. And we see that the delta function does not have v old in its argument, but a factor times v old, and then we need to use this rule for working out the delta function, and we obtain then the following result. So here is the result. First we have a term 1 over 1 minus gamma delta t, which comes from working out this delta function with the 1 minus gamma delta t in front of the v old. And this v old here has been replaced by the remaining arguments in the delta function, so that's v plus gamma v minus r delta t. This is the new v, and the old v is related to the new v in this way, and I still have the probability distribution, the Gaussian probability distribution here, and I'm left with only one integral because the delta function has been used to do away with the integral over the v old. And looking at this equation, we immediately see that it's useful, because delta t is taken to be small, to do a Taylor expansion for the p. So that is the next step, and we do that Taylor expansion to second order in the delta t. So here is the result. This is the 0th order term, which I find by taking delta t equal to 0. Then here is the first order term, and here the second order term. All the p's and its derivatives are all evaluated at v and t, except that I have not mentioned those, I've not reproduced those arguments explicitly in the last term. We are going to work out all the terms to order delta t. So let's first look at the first term, which is multiplied by PR delta t, and then we integrate over dr delta t. But because we make always one step r delta t, this probability density is normalized. So that means that if we integrate over delta r, over r delta t, like we do here, we always get a result 1. And because there's no r delta t dependence in this term of the integral, the first term we obtain, the 0th order term, is just pvt, because the integral over the remainder just gives us 0, it gives us 1. And then, if we want to work out everything up to order delta t, we see that we can multiply this by 1 plus gamma delta t. The next two terms each give us contributions which themselves are at least of order delta t. So this delta t correction will give at least an order delta t squared. And because we work consistently up to order delta t, this term will not have any effect on the next two terms, not to order delta t. Now we consider the second term, and first we have a gamma v times delta t, which I've copied here, multiplied by dp dv, and then we have again the same integral of a normalized probability distribution, so that gives me just the 1. This term here with the r, the probability distribution here is Gaussian, and it's symmetric, so if we multiply it by r we get an anti-symmetric integral, so this after integration will lead to 0. So this is the complete result that we obtain from the second term, which is the term to first order in delta t in the Taylor expansion. So let us continue with the second order term, from which we first obtain a contribution gamma squared v squared delta t squared over 2, and then again we have an integral of the second derivative of p multiplied by a normalized Gaussian, so that just gives me a 1. The term which is linear in r vanishes for the same reason that this one vanishes. We have an anti-symmetric integrand, and then we have an extra term, and that term is equal to delta t squared over 2 times d squared p dv squared, and then we have an integral of r delta t squared. So the fact that I've put the delta t squared here means that I can leave it out here. Then we have a p r delta t, and we integrate over that r delta t. So this is the second moment of my Gaussian distribution. Now we have seen above that this in fact it can be written as the expectation value of r squared times delta t squared, and we had seen that that was q over delta t, and the q had the value 2 gamma kbt, and therefore we see that the second term acquires the following form. It is gamma times kbt times delta t times the second derivative of p with respect to v squared. Now there is one final step we need to perform. We have the difference here of pv taken at t plus delta t and pv at t if we take only the first one and we bring it to the left hand side, and that's obviously the first derivative of p, and so we arrive at the following equation. An equation which gives us the time derivative of this probability distribution, and it depends on the first derivative here and the second derivative of p. In fact, this term, of course, when I work it out, it generates two terms. One is the term here with the gamma delta t. That's the term when I take the derivative with respect to v, and when I take the derivative with respect to p, I get the second term here. This equation is a famous equation, and it's known as the Fokker Planck equation. In order to check whether the Fokker Planck equation makes sense, we look at a stationary solution which we find by taking the time derivative of p equal to 0. In that case, the right hand side of this equation should be 0, and it is solved by the following expression. PV is c times minus v squared over 2 kbt. If we had included the m in our derivation, we would have had an m in this equation, and then it would be minus mv squared over 2 kbt. So what we have obtained is in fact the Maxwell distribution. It's the Boltzmann distribution for the speed. And we have obtained that for the special case m is equal to 1. For the case where m is not equal to 1, we find the following Fokker-Planck equation, which includes an m in the first term in the denominator and an m squared in the second term. So finally, let me summarize what we have seen. We have tried to formulate an equation of motion for heavy particles that feel an influence of many light particles which collide with the heavy ones. There will be an average effect to drag down the particles, and that's captured by this frictional force of the heavy particle minus gamma v, and on top of the frictional force there are random kicks, and they are represented by this random force r. And the random force will be different each time we start a new experiment. Obviously, it's a random force, but it has some statistical properties, and we can express those in terms of expectation values, and the expectation value is always interpreted as an average over all the possible realizations of the random force. So the first thing we can say is that the random force, the average value of the random force over many realizations is 0, which tells you that there is no bias in the force, in the random force. Any bias is present in the frictional force. Secondly, there are no time correlations, so the heavy particles move quite slowly, and before they significantly change their direction or their position, there are many collisions, and therefore these collisions averaged over some time interval are not correlated, and we express that by this delta function for the autocorrelation function of the random force. And finally, the distribution of the random force is assumed to be Gaussian, so the p of r is given as e to the power minus r squared divided by twice the average value of r squared. We can make a step further if we really solve this equation of motion. That's possible, and the solution is given here. Vt is v0 times an exponential decay with time constant m over gamma, and then there is a second term which involves the random force. If we then take the average over all the realizations of that force, it vanishes due to this assumption, and we are left with a velocity that decays to 0. So this solution only sees the effect of the friction. On the other hand, if we take v squared, then we see first of all the effect of the friction, but then we can use the fact that we have a result for this r squared, and that gives rise to the second term here, and that's the effect of the fluctuations. That's the noise that we see on top of this decay. If we wait infinitely long, then all the decay has gone, all the decaying terms vanish, and what we are left with is then q over 2 gamma m, and we know that we can relate v squared, it's related to the average kinetic energy, which is kBt per degree of freedom, and we find this relation between gamma, kBt, and q, which is the amplitude of the force. Recall that it occurs here in this delta function. We can also find the distribution of all the velocities in a system. That's called PV of t, which is the probability density for finding a particular velocity v at time t. In fact, we have derived a time evolution equation for this probability density, and that's written here. dp dt is equal to gamma d dv of v times p plus gamma kBt times the second derivative of p with respect to v, and this equation is called the Fokker Planck equation. If we look for the stationary solution, we put the left-hand side to 0, and it turns out that the solution is then given by the Maxwell distribution, and therefore this equation describes how in a system a non-equilibrium distribution of the velocities evolves towards the Maxwell distribution.